important. Yes, yes, yes. So, and also for your reimbursement. But even when you are not reimbursed by cost, just sign it, then you make everybody happy. Okay, great. So nice to see everyone back here for the last session of the conference. And we start with Nikita Sokolova. I hope I said it correctly. And yes, so she will tell us something about Rosetta Stone for Wilson line defects. Please go ahead.
Hi, everyone. Good afternoon. Thank you for the nice introduction. So I will be talking about our work, which we've done with Julius, who is a postdoc at ENS Paris. And for this project, we have a poetic name, which is called Rosetta Stone for Wilson line defects. I think for now, I will leave the name how is it, and I hope that during my talk you will see what we meant by that, and then by the end of the talk you can judge like how you like the name or if you don't like it. Okay, so I will start with a gentle introduction. So first I will, because of course I will talk, as you understood from my title, we'll talk about the line defect, but I will focus first on n equals to 4 super-Yang theory, which you all know and love. And I will discuss a bit the spectrum of this theory. Then I will try to introduce the line defect, which we are going to talk about in more detail, because we will just discuss the spectrum of this line defect. So to start, of course, everyone knows about n equals to 4 super-Yang meals, and it has many nice features which we all appreciate. So first of all, it has many symmetries. It is super symmetric, and it has conformal symmetry, which we would like to explore. So it's a good playground for us to test these properties. And also it has a lot of other features which nicely combine within this model. So first of all, in the large n planar limits, famously we have contribution only from the planar diagrams. And for the spectrum, it means that it is dominated by the single trace operators. And what integrability tells us is that the spectrum of single trace operators is known exactly for this model. And of course, we have a duality, a DS-CFT, so a strong coupling. We actually can understand more the string theory, which is dual to our CFT. And then if we understand n equals to 4 better, we can say something about string theory and the curve background, which is a very nice goal, which we always have in mind. Yeah, so to discuss the spectrum, which you've seen many times of n equals to 4 super-Yang meals. So here, first of all, the plot over here is the numerical spectrum for n equals to 4 for single trace operators for all superprimary operators up to bare dimension 6. So in our and this solution is obtained by the quantum spectrum curve numerically. And so here on the plot, you can see the spectrum. You see, so it starts with, so here, of course, we have a coupling, which goes from 0 to 5, coupling G. And then we have our spectrum up to the bare dimension 6. And then we just solve the quantum spectral curve for all the states, which have different types. And there are like fermions, bosons within the setup. But so for all of them, we run this numerics and we see that this flows like this. So these are just the solutions which we get from the quantum spectral curve. Yeah, just to be precise, actually over here, it is just a subsector, only left-right, so-called left-right symmetric states of n equals to 4 from the quantum spectral curve point of view are plotted, but the plot for all states, it will look very similar. So I decided to just keep this simpler plot for representation. Okay, so this is what we get. And then, as I told, at weak coupling, of course, we have like the single trace operators, which can look like this. So we have a field of n equals to 4 And then we can have, of course, derivatives applied to them, and then our operator will be like some combination of such fields. And then, okay, so of course with states, because we're working with supersymmetry, and we discuss so all of these are like super primary states and the super multiplets. So here, we describe them by their quantum numbers. So we have, of course, the scaling dimension. Then we have 2 spins for n equals to 4, and then we have 3 R charges. And then, okay, so what we see here. Okay, and then we see how they go to strong coupling, and immediately what we can see from this plot is that, and it is also prediction from string theory, that strong coupling, they should grow like this. They should have lambda to the 1/4 behavior, a strong coupling, and then we will have this integer parameter delta, small delta, which is a slope of the curve, and each has a meaning of a string mass level. And indeed, our solutions, we see that they all grow like this, and then we see clearly the formation of these bands, which correspond to different masses. Okay, so this is there's just a solution which we get from quantum spherical curve, and as you probably heard before and from Paul's talk yesterday, we always work with states in an abstract way. So we describe them by the set of Q functions, and we are losing a bit the notion of these fields which are inserted, and also we can just treat them more generally, and then we just get the solution. So okay, so this is the setup for n equals to 4. But here we are actually going to go to the line defect, and the reason why we go to the line defect, it will be clear for you later. Why there was a particular interest of us in this defect. But okay, just to start introducing it, so we have a defect in the bulk n equals to 4 theory. It is a Wilson line, but we also have a coupling of one of the fields of n equals to 4. And also because we, in R space, we also have a direction, and we can choose one of the directions in R space to be parallel to the line, so that we have a notion. So our 6 fields of n equals to 6 scalar fields of n equals to 4, they break their symmetry. So we have one field phi parallel, which is parallel to the line, and then we have 5 more fields, and SO5 rotation symmetry, R symmetry. So then our symmetry breaks, and we have 1D conformal symmetry along the line. Then we have SO3 rotation around the line, and we have SO5 R symmetry. And so these are like our scalar fields which we have. And okay, and then we can insert operators onto the line, and we consider such observables, operator insertions, and then it was shown that such correlation functions only defect actually is a CFT, is a 1D CFT that was shown in this paper. So for example, we can consider, of course, our favorite observables 2-point functions, 3-point functions. And so here is an example. We have a 2-point function of phi parallel, which will have this law. And then, of course, we were working with scalar dimension of this phi parallel field insertions. And of course, the same is getting generalized to the 3-point functions or structure constants. So we can have such insertions, and then they will have some corresponding structure constant in the defect CFT. Okay, so to see what's going on, so which operators insertions we can have. So we can, of course, we have scalars as I described, and then we can also have corresponding fermions with broken symmetry. Same about the field strength. Because of the line, because of the breaking symmetry, you can get these components, and then you can have covariant derivatives, which is like one of them is along with the line defect, and another one is just SO3 derivatives. So these are like the letters at weak coupling, which we call the lexicon. And then corresponding actually lexicon is strong coupling, because we will have some dual string descriptions. It corresponds to fluctuations on an IDS2 worldsheet. And so over here, they also have like a basic letters to corresponding to the modes. So we have 5 bosonic modes corresponding to S5 fluctuations, which it will be like Y, letter Y. And then we have bosonic modes. And we have fermionic modes. And also we can also have derivatives along the defect. So in principle, we have these 2 languages. We have language at weak coupling, language at strong coupling. Okay, so we will see. Okay, so back to weak coupling, because we have supersymmetric theory. It's like in our line defect is actually has some supersymmetry. So all our operator insertions, like the simplest insertion is of course phi m and phi parallel. They all belong to super multiplets in this theory. So let us say we pick up an operator and insert it to the line. So we have a set of quantum numbers corresponding to this operator, of course, the scaling dimension, spin, and R charge. Okay, so going back to the scaling dimension. So due to supersymmetry, some of the scaling dimensions will be protected. So for example, for this insertion phi m, it will be just 1 because it belongs to beta 1 short multiplet. And then phi parallel actually belongs to one of the long multiplets. So its scaling dimension, it will depend on coupling and will flow. And the list, all the super multiplets and whatever is protected or unprotected, you can clearly see by the unitarity bound. So you have your spin and R charge, and by unitarity bound, you see if your multiplet is protected or unprotected. And though all the superplets for this model, they were just known, luckily, by this paper. So this is information which comes for us, and we see this picture. Okay, so and then we have at weak coupling, and actually we can have all these super multiplets, all these various super multiplets in the game, like at weak coupling. However, a strong coupling, as it was shown by Ferrero and Menaghelli, so actually all our fields come only from one single super multiples beta 1. So we have just 3 fields from which we construct our operators as strong coupling. So these are the quantum numbers of these 3 letters which are there. So first one, so this is spin, 0 spin, 1 is dimension, and then this is R charge, 0, 1, Dynkin labels. And then we have like 3 fields over here. 1 spin 0, spin 1, spin 1, 2, spin 1 half, and spin 2. And then basically strong coupling, we know that all our operators can be constructed only from these 3 letters, so-called. And then, of course, we can also add the additional derivative along the defect. So, and then this is so-called a simplification at strong coupling, which we have, because we don't, so all other super multiplets, they are just not there. They do not contribute. And we're left just with this simple picture of one super multiplet. And okay, so in comparison with much more complicated weak coupling, we have, so for example, this is like the multiplet which captures phi parallel. So these are all super descendants within this multiplet. And you see there is like, even for this one of the multiplets, we have a lot of letters, and we can also address with derivatives and so on. Right, so we can already have an understanding that we have like a lot of possible states at weak coupling, but they have some kind of a reduction in strong coupling, where we have only one multiplet. And and actually what we want to do next, we actually want to count how many states are there, so how many like super conformal primaries are there at weak and strong coupling. And in order to do that, you should use the counting procedure. And I will probably not make it clear in this talk how one can do it, but I recommend, and that's how I learned these techniques. I recommend these lectures by Abhijit Gadde. at Young Researchers and Integrability School 2020. And then over here, he explains very nicely how you can do it, starting from quantum mechanics. And then, so basically what you do, like roughly, is that you have, for example, one letter from which you can create words in your dictionary. And then what is your partition function? Okay, for bosonic letter, it's like this. And then you can rewrite it as a pletistic exponent of a single letter, which also has this explicit formula. And then, so basically the message is that if you know your single letter partition function, you can understand what is your full partition function. And then for the fermionic letters, there is some modification, of course, because you cannot construct more states. And then the modification, it will be slight modification, but you also can write a formula. And also you can incorporate global symmetries, like you can just write down a character of your state, and you will describe it by a set of characters you have, and then a single letter partition function, which you can just write down if you know your representations. And then, so here, more precisely what we have is, for example, a strong coupling. As I already told, we have just like one multiplet, and then we just have these three super descendants, and for each of them, we associate a character. And it will be like our single letter partition function, meaning which single letters which we can have. And then over here, we take into account that they have a derivatives applied on the top. And this is like single letter partition function, a strong coupling, but at weak coupling, we have much more super multiplets. We have actually infinitely many super multiplets at weak coupling, but it's okay. We can write their single letter partition function. Another complication actually at weak coupling is that, so our operator insertions, they you should respect their order in which they're inserted. So you should understand that we also have like our Android representation. And for this, it was already done in Christopher Superian Mills. There are many papers on this topic. One of these papers is like by Dolan, but there was also Anani and others. And in order to incorporate like n equals to 4, you need to modify your pletistic exponent a bit, which I will not describe how, but it's done. For us, for our purposes, it was already derived. So it is just analogous of pletistic exponent. But because we have a Wilson line, there is actually like a nice modification you can do in order to incorporate your geometry that you have a Wilson line defect, is you just introduce a separate Wilson line defect as a parameter in your single letter partition function, and you can take like a first, you can take derivative with respect to it and then take like the linear coefficient, and then again you can get your numbers. Okay, I'm getting too technical here. So let me just move on, and let me say that this counting actually has been done not by us, but by Ferrer Minaghelli already in 23. So this is just the numbers at weak and strong coupling which you get. So this Q represents dimension, bare dimension at weak coupling. So how many states do you have with a given bare dimension? So with dimension 1, we have one state, and we have 2 states with dimension 2, 6 states with dimension 3, and then they start to grow like crazy, and then you see that the growth is a lot. And then the strong coupling, you write down the same partition function. So it's again, we have one state with dimension 2, 2 states with dimension 4, and so on. Okay, you see it's much simpler, you know your numbers. But we were kind of puzzled like how to connect these two pictures together and to understand, you will see later why we're thinking about this, but we want to understand, okay, so what happens between weak and strong coupling, how states go to one to another. And okay, so in order to actually understand what are our dimensions, which will be non-perturbative, we again rely to our favorite technique, quantum spectral curve. And to be honest, we will just jump almost directly to the solution, but to just give you a bit of introduction how it is even possible, like if you have some defect, how you can do quantum spectral curve. So for example, like Wilson loop, so here, of course, So one should basically see, so we have like operator insertion, right? We have a Wilson line and we have operator insertion. So usually we have, of course, a single trace operator on a normal n equals to 4, and it will be correspond to closed pin chain. So here, because we need we have like an open operator which is inserted to the line, so it will correspond to spin chain with open boundary condition. And you can write down this correspondence, and of course, basically you can get a Hamiltonian at one loop, so which will be like your known Minahan-Zaremba Hamiltonian plus some boundary terms, which will correspond to coupling to the line, and it was derived in this paper, beautiful paper, and so you can get your anomalous dimensions and wave functions at one loop. It is not known for, just to say, it is not known for all subsectors. It is known only for the one of the subsectors. But for us, like for example, you can see that you can get like one loop state, so you can get dimensions and also the wave functions. And they will look like this. It will be some combinations of the operator insertions and so on. And given this Hamiltonian, okay, so how we can jump actually to the n equals to 4? So there was some, so actually we noticed something. So there was an observation which was done during this collaboration that you can actually, there is like some mapping you can do to n equals to 4 superior mills at the one loop level. So basically your one loop dimensions is exactly one loop dimensions for n equals to 4. And then the quantum numbers look map to each other in a complicated way, like this. So you are having your quantum numbers on the defect, and then you can find that it will map to this state in n equals to 4. So okay, so here it's a bit complicated because it's labeled in this oscillator notation and equals to 4. So probably let's not study in detail this particular mapping, but there is just some understanding. There is like one loop level map to n equals to 4. And then actually for the purpose of this talk, it was just useful in a way to guess the solutions of quantum spherical curve, because how it usually works, you just try to guess them and your ansatz and then solve. So for example, like let's consider this state, like to see like roughly what we're getting. So we have actually, so now we did not have any notion here, like we have the scalar state in the defect, just zero vanishing quantum numbers, and then we actually see that there is some notion of twist, because their dimensions, how dimensions map, we have different twists corresponding to the states, and these twists are more like in n equals to 4 twists. So we have like, so for dimension 4, per bare dimension 4, we have like different twists of the solutions, which are just borrowed from n equals to 4, this notion. Okay, so this is just to introduce that we have a twist on top of this on the solutions. And then, unfortunately, I don't have time to describe in details how this can be done, but you can solve the quantum spherical curve numerically. So you get this very similar plot to n equals to 4, but with some important difference, which probably immediately obvious from the plot, but or let's discuss again. So this is like the all scalar multiplets. So they have vanishing quantum numbers. Again, the coupling goes from 0 to 2 in G, which is and then we have like in some bunch of initialized operators here. So up to dimension 3, we see all the operators which are given by the counting. So here we indeed have one state at dimension 1, two states at dimension 2, and 6 states in dimension 3. So it's according to our counting, we capture all super multiplets at 3 coupling. At 4, we unfortunately don't find all solutions yet, because you see there's a lot of them. But for our purposes, we grab the ground states, and then we keep track of them from weak to strong coupling. And you've seen the difference from n equals to 4 is actually we arrive to integer dimensions, which was expected according to the counting. So we need to reproduce the numbers which are given, which you saw in the previous slides, that they're just integer dimensions through coupling, strong coupling, and then you have degeneracies, and then we match the counting as well by the conspectral curve. Okay, so here actually you probably see what we want to do. We want to understand how the degrees of free, if we if you can see in more details, what are the correspondence between weak and strong coupling in terms of the fields in which operators are written. So here we of course have just like a general solutions, but then we want to understand from which fields at weak coupling they're made on, and to which fields a strong coupling they land. And if we can, in principle, find some patterns which would explain for us this picture, this we were up to, and this we were trying to do. So that is my last part, which is called constructing the map. So let us try to see which steps we try to take in order to do that. Okay, so here, of course, like I described to you, like this counting procedure and then single letter partition functions. So we have a notion of single letters, which go to the single letter partition function, and then so you have all these super multiplets. As you saw, it we coupling infinitely many super multiplets, which gives you the single letters. And when, so this is just the raw quantum numbers, and we want to see from which fields the coupling they're made of. And then, so for the first operator, as you saw, it's like phi m. Then the next one is phi parallel, the first long multiplet. And then, okay, for the next one, you can also see the exact form, this F hat, which is derived in this paper. And then also we are just trying to construct here, like this F star is just, we are saying what could be possibly the states with these quantum numbers. It is nothing special we do, consists from the single fields, and with any derivatives applied, we just write the general form of it. And okay, so now we are, so basically at the weak coupling, we see that our single letter is are just these. They are just given by the quantum numbers of the supermultiplets. And so here we are saying we want to take single particle states, and we see where they go to the strong coupling. And this is not so easy because we have completely different alphabet over there. And so there was some things which are already known in the literature, like so first of all, it was because so phi m forms the B1 multiplated weak coupling, and this ym forms a strong coupling. And then this was already like where 5 parallel maps, it's already shown in this paper. And then, so where other superparameters go to. So then, of course, we expect like single particles to go to, so which will be like the ground states, because it is just literally the super conformal primaries. They will also go to some ground states, a strong coupling. And then we consider, so operator, so what this is the partition function at strong coupling with spin j. And then we don't specify the dimension of it, but we see that what is the lowest dimension and which content it has. So here for spin one, it's just the raw partition functions which we write down, which is actually, I did not mention it in such good detail, but you can also track additional fugacities, meaning from how many of single particles your state is composed. A strong coupling, and then also if there is an action of supercharge on the top, you can also keep track of it. So they see that okay, so this ground state is like this. So, and they can see that there is some mapping which we can do that. So they see that our single letter is composed to has this dimension 2 j plus 1, so dimension doubles. And also we also understand from how many particles it is composed, and we have an action, we know how many supercharges act on this ground state with spin at strong coupling. Okay, this is pretty nice prediction because, and then we want to, yeah, so probably let's go back to weak coupling and see, and so there we're just, as I already described to you, so these are the letters, these were the two mappings which were established, and then we have some operator strong coupling, which is just like the operator, which will correspond to whatever this dimension, this number of particles, this number of supercharges acting on it, is strong coupling, and we just denoted that F star because we're not really knowing the linear combination. We just know how many particles are there and how many supercharges are there, and that weak coupling it also corresponds to this. Any like master state which you can get from that quantum numbers. Okay, so then basically, so our main prediction that the dimension for single particle states at weak coupling doubles the strong coupling. This is like one of the basic prediction we do, apart from the construction from what it is getting constructed, and we see that indeed, like this is the new state which we update from quantum spherical curve, and they are with the spin, and they are very helpful for understanding if we are indeed right, because we didn't have the states before we constructed the map, so we thought, okay, it will be kind of a confirmation for where single particle states at weak coupling go. And all of them indeed go to just double their dimension in strong coupling according to the prediction from the partition function. And then, okay, so we have this nice match. And good. So, but then of course, single particle states are nice, but what about more particles? Is anything special? And in fact, there is very special picture, which we have the two particle states at weak coupling. And the first observation was made back in Fermi-Nagelli's paper. So they just, so here, this L parameter, it tracks the length from how many letters your stated weak coupling is made. And so we list two particle states. So you see their partition function grows ridiculously slow. So this is the first observation which we make. It's so simple that you can try to understand it better. And we thought, so we would like to track also the contribution of supermultiplets. And so we also tracked supermultiplets which correspond, which give this partition function, and we found this structure. So basically, so there is like two supermultiplets, and then like this, if supermultiplets appears and just gives you the tower of states, and then another multiplet, so these two multiplets appear, they give you the tower. Then at dimension 4, we have a third supermultiplet, which gives you the tower of dimensions. Okay, so this is like a very simple structure. So we wanted to see if it means something, and then about like the map, if they can tell where these two particle states go with strong coupling. And then, okay, so you can also try to construct from which fields they are made, but this you just write the most general form. Because of course here you also see that it's just a squared content of one of the supermultiplets. And then you have just derivatives on top applied. So in principle, you can guess how this state looks like in terms of fields, because it will be just squared superprimaries with a bunch of derivatives applied. And so we just write this. It's a general form. We don't have a constants between these different constituencies, but roughly the content of it we can see by this surprisingly simple structure of L equal to 2. And then, okay, so actually what we see at strong coupling, we want to do the same trick. And we want to okay, the point is we can't really restrict ourselves to like two particle sector at strong coupling. But what we can see, we can try to find patterns, and there was one pattern which we found. So this is just a raw partition function strong coupling for various dimensions. So this is dimension 8 partition function, and it has like all contributions written with the supercharges also contributing to the partition function and so on. And you see, so we kind of see like it's not really a chain as we saw before, but we see like a tree. So we notice that there is like this tree. So there is this one nice state, dq to the power 4, so which is actually is just like the fugacity content of this seed of the tree is like is doubled fugacity content of two particle states at weak coupling. And so we suggested this state, which forms the tree, which would correspond to the one at weak, at the two particle state at weak coupling. So this is like the head of the tree, and then this is, and it kind of creates like for you other states acting with derivatives, but multiplicity of them will be higher, and then we don't really say about them, but we see that the head, so the two particle states, the map superprimary, the map to this state, and it has this content. So it has this number of particles and this number of supercharges acted. Okay, so this is the map basically we propose, and basically we just try to map the fugacity contents at weak and strong coupling, and then we just, and also to the top of just like the content, we try to see what is going on with derivatives, and then probably these details are not so important now. We just try to, but we see like, so we can construct a map from one two particle state to another. And we, based on that observation which I showed on the previous slide, so this is what explicitly the proposal for the mapping. Okay, so this is like the proposal which we can make, which which we did only for the two particle states at weak coupling, but we did not do it for more than other particle, for three particle states and so on. Okay, just to speed up, actually, how we can test this map, because I showed you all the solutions of the quantum spectral curve, and okay, so what are two particle states in the solutions? And in fact, on the top, we found a nice resemblance that we found that the solutions of QEC, which are restricted to one particular twist subsector, which is twist 2 subsector, solutions of Baxter equation of that subsector, they grow precisely as this very nice partition function which I showed you, like this 2, 2, 3, 3, 4, 4. These are the growth of a twist 2 sector. And then we just restrict essentially to the twist 2 sector, and we see nice features of it. If indeed we see that our prediction of dimension is satisfied for the subsector, and indeed we see that two features of the plot. One feature of this plot is that we don't see self-crossing. So states they flow smoothly from weak to strong coupling. And then a second prediction of us that all dimensions with dimension 0, they will go to 2-dimension 0, and then okay, it matches for all examples which we study here. And on the top of this, like if we restrict to this subsector, there will be no self-crossings, nothing. So the spectrum is smooth, which is quite surprising. Yeah. So then, okay, so we have these observations. And so here we see like what can be done more, and if it's possible to do anything more. And then, okay, so we saw that two particle sector is nice, and in principle, if introduce like a notion of two particles at weak coupling, it makes sense because it corresponds to a simple subsector. But then, so is that you like why this two particle subsector is so nice? Like, so why it flows so smoothly, and why we can see good structure? Like maybe there is some hidden understanding of all these features of this theory, and maybe you can do like not also the partition function calculations, but maybe you consider superconformal index to maybe unveil something more, but maybe not. Yeah. So, and then also there is a nice interplay with these papers which appeared this and last year. And so there they consider a totally different, a bit different setup, because they don't have supersymmetry, but these are just flux tubes. And then these authors, they also consider kind of if you can make a map from weak to strong coupling, and in particular how your states will grow. And then, but for them, the point is they don't know, of course, the so well spectrum from integrability. So and then they try to understand if they can construct such a mapping. If, like, for example, if you have some states at weak coupling, how they will go to strong coupling. And for them, it's interesting because, like, if you start with some spectrum at weak, it's important to know which dimension you go to strong. And so with this, we kind of wanted also to understand if for our super nice, super symmetric setup, we can shed some lights. Right. Yeah, so so almost done. So maybe so some outlook with regards to first of all, like in general cartography. So so the point is, okay, we observed like some nice feature of the both partition functions and the spectrum restricted to some subsector. And then, okay, so is it like how to specify more concretely, like interplay between the existence of the map and then how spectrum grows and where it grows? So even for higher particle states, if we consider 3 particle states in this theory, like is the structure simpler or not? I would say no, but I would say that only 2 particle subsector is nice, but it's something which we don't know. Like we need to consider more particles and then to see maybe what is the interplay with our solutions from even asymptotic beta ansatz to see what we can say. Yeah, so I think I will finish here and leave this last slide for further questions or something. And thank you very much for your attention.
Yes, thank you very much for your nice talk and also for being perfect on time on the second. So we have time for some questions.
So here you did this whole analysis for Wilson line defects, but is there anything special about those? Or, I mean, this whole program you would carry through for any kind of defect, I suppose?
Yeah, so this is one known defect for which this whole machinery of quantum spectral curve is done. So, and then the nice feature which I tried to highlight that the spectrum goes to integer dimensions. And so that you can see at the strong coupling, it's a rare case where you also can see that I have this super multiplet and this is my fields. And then dimensions, you can consider partition functions. Dimensions are integers. You can have a simple partition function there. Even for the bulk n equals to 4, your states will grow to lambda to the 1/4, which are not so, you cannot touch them so simply. Other defects that are just not known so much from integrability. You cannot try to see anything, maybe something you need to do more defects and see if you can say something.
Okay, great, thanks.
Are there any further questions? No, if not, then let's thank Nika again.